Hi, this is Matthew Thomas at the University of Virginia. I'm going to be reviewing the Broad Institute's exact browser and other methods of looking at variant frequency in the general population. I'll start with exact because it's the most comprehensive way to look at population data for particular variants and has a very user-friendly way of doing so. So this is a home page where you'll see a search bar right here where you can search for a particular gene of interest. If you know the transcript, you can search for that. The variant location using genomic coordinates, and then a region of the genome of particular interest as well. I'll be focusing mostly on doing gene-specific searches, variant location searches, and the examples that I'll walk through today. For more information about the Broad exact browser, you can check the About section where they summarize the purpose of the browser itself. Basically is a conglomerate of a bunch of different exome sequencing data from a bunch of projects that many of you are probably familiar with, including the 1,000 Genomes Project, the ESP, the Exome Sequencing Project, and others. It's important to keep in mind when you look at this list that some of these are patient populations, affected patient populations of participants. And so you're not necessarily getting only healthy individuals. Most of these tend to be adult onset disorders in the affected populations, like type 2 diabetes, individuals that have had heart attacks, schizophrenia, and other more multifactorial diseases, but it's something to keep in mind. It's a data set of over 60,000 individuals that are approved through their filters. And the Broad Institute used a very complex pipeline to systematically approve each of the variants or data. Next up, you can check the FAQ, which is another source of giving you information about what the Broad exact database is all about. The things I wanted to point out about their FAQ is that you can't look at specific phenotype data for most of the individuals who contributed data through the sources exact is using as part of their analysis. They've also made efforts to make sure that this database excludes individuals with severe pediatric diseases, which again has to do with where the data is coming from. This also summarizes what the genome build is for the exact data so that when you're searching for a variant, you're using the same genome build when you're searching their database. And then again, here's more specific data on the populations that are represented in the exact data. One of the particular strengths about this database is the representation of other ethnic backgrounds that have typically been less widely used in some of the databases that have been previously available. And then specific numbers on the cohorts that are represented in the exact data. And I won't spend any time walking through any of these individually, but just know that it's there in the FAQ. For a bit more information, from a few months back, there's a blog post from the MacArthur lab. MacArthur is a PI involved in the creation of this database, and they walk through a bit of the history of the exact, the construction of it, where the populations came from, so starting with 92,000 individuals, and then using their complex pipeline of variant interpretation analysis to bring that number down to about 60,000 individuals, and then you can see an example of FBN1 of how they sort of summarize the data, how they interpret coverage, and talking about a few different aspects of this that I won't address in this video. I will provide a link to the FAQ, the About section, and the blog post for the MacArthur Lab summary of the exact in the comment section of the YouTube video. So I'll walk through 3 examples of variants and how they appear in exact, and then also the other larger population databases that exact frequently pulls from. It's important to keep in mind that any data that you see from the ESP or 1,000 Genomes Project may very well be represented in exact, depending on whether or not the quality of that variant call passed the filters that exact uses. But this is a database that some labs choose to use and some labs don't report on the, that's not what I want to say. The Broad Institute hasn't published their paper yet on the development and outcome of the exact browser, and that is expected to come out sometime at the end of in the winter of 2015. So when you're searching for a variant, there are a couple of different ways to do so. I'll pull up a lab report to give you an example of what is a few ways of doing that. So I'll start with a MYH11 gene variant found in a patient of mine that had an aortic aneurysm that appeared to be familial. As you can see, your variant nomenclature is up here, and you can search the Broad database a few different ways. The first I'll do is just typing in MYH11, and then you would just click on that and it would search for you. I've had that pulled up because sometimes the loading time can be a little bit delayed. And this is what the MYH11 gene variant page looks like. Obviously, it starts with the name of the gene, the number of variants that have been called. You can see that the full number of calls is different than the number of variants that are going to be present, depending on if it passed their filter for quality and coverage. It links directly to the UCSC browser and GeneCard's OMEM, etc. And so this is first a coverage map of how well each exon highlighted in blue is covered. Coverage is anywhere in this gene, it looks like, between as low as maybe 10 toward the end of this exon to as high as 90 to 100 for many of the other exons. And then you start walking through a list of all of the variants that have been identified in the MYH11 gene. Again, the way it's represented is a variant nomenclature, which is starting with the chromosome and then the genomic coordinates. Again, and then the change from the wild type to the variant. And then you see the chromosome position. The consequence is typically showing you the amino acid change and sometimes the splicing difference, which is represented here. The next is whether it passed the filter. You can include non-pass variants that were filtered out by clicking this. And then you can see the annotation, which is typically the type of variant it is, which will be either missense, anonymous, an end-frame insertion, stop gain, let's see if there's any other end-frame deletion. So there's a lot of very useful information there. And you can see how many times the allele has been seen specifically, that allele number, the number of homozygotes that have been observed with that particular variant, and then ultimately the allele frequency, and then a graphical representation of how common that allele is. So one way to search for the variant that you found is by the amino acid nomenclature. As you've seen, it does represent here each of the variants that they've observed and then what that amino acid change would be. The thing to make sure of is that you're looking at the same variant, which isn't always obvious. The transcript they use is usually designated here, and that's the primary transcript, but that's not always the same one that the lab uses, and it's not necessarily easy to sort that out based on just the exact database and your lab report. So starting with the variant search itself. So this is an arginine 1535, and so you can simply do a Control F or find. All right, so using this search function, arginine 1535, it did not pick up that variant. I'm just going to double check. Okay, so it didn't find it that way, but because it's possible the lab uses a different transcript than what the exact defaults to, we're going to try searching another way, and that is by the genome coordinate. Finding the genomic coordinate typically requires using another program, another open source website. We tend to use Mutilizer in my experience, and the way you find out the specific genomic coordinate is by entering um, the transcript and the specific cDNA variant. And so for this particular MYH11 variant, we know the amino acid location, but you need to go into the text to find the cDNA one, which is designated here. And then you also want to know what the transcript is for this variant. Some labs put that in their methodology, and so for MYH11, the transcript that this lab uses is listed here. And so I'm going to pull that from another location that I've already copy and pasted, and it converts that to a cDNA location. Now you'll notice that instead of G to A, it's C to T because it's using the reverse strand. And so what you can do with this information is take this specific variant location and then search that in the exact bringing that variant in this. Whoops. Probably be helpful if I search the right variant location. So you paste in the variant location here, and lo and behold, there is a variant designated at the exact same genomic coordinate as the one we're concerned about. So arginine 1542 glycine, which is different than what's designated by the lab, again because of difference in the transcript that's being used. And so we found our variant, and you can see here it's chromosome 16, that's the location, pass, it's a missense. This is how many times that variant has been observed in their population. Alleles of it have been observed, and this is basically the number of participants times 2, because it's the number of alleles that have been counted at that particular locus. And then this is how frequent that is. So we can learn more about it simply by clicking on the link for it. And you see specific information about that given variant. You see obviously the nomenclature, whether it passed the filter, its DB SNP number, its allele frequency for the total population available in the database, number of alleles seen, actually has a link to ClinVar and UCSC for that specific location. And then you can see the population frequency, which is probably the most valuable portion of this. And so you can see the frequency in people of European ancestry, non-Finnish, Asian, Latino, East Asian, African, etc. And then so you can find out what is the frequency and what's the race or ethnicity where the variant is most common. It looks like in this case that is going to be the other category, which doesn't have necessarily a lot of alleles, but you also can see that it's fairly, it's around the same frequency in other ethnicities as well. You can see how high the quality was for a given call. So if you look at all individuals that were sequenced as a part of this database and other sources and their pipeline, what the depth of coverage is for that particular location. We generally consider 20 to 30x coverage to be depth to be useful, but this actually shows you what that looks like, so you can know how trustworthy a call is. And so this is one example of how a variant will show up in the database when it's covered. I'll review variant interpretation for 2 more variants a bit more quickly for the sake of time. The first one will be a variant found in a patient with hypertrophic cardiomyopathy. This is a separate lab than the first one, a different lab than the first one. You can see again the gene that was queried, or the variant and the gene that was found, then the variant nomenclature, and then when you get to the methods section, you can see where the specific transcript information is located. So if you put the gene into the exact browser and search for it, you will receive a page like this after it loads up. Same level of detail about the number of variants found, including those that were filtered out. A graphical illustration of the coverage, average coverage of each of the exons of this particular gene, MYH7, and then a list of all of the variants in a table below. In this situation, we're looking for a variant with the amino acid location of 548, again presuming it's using the same transcript, which often happens but not always. And in the first example from MYH11 we did not see that. So we'll search two different ways. So we'll search by amino acid first. So we'll do Phi 548. And that did not show up. Since that didn't happen before, we want to make sure that we're not missing anything. So we'll go ahead and look at what the DNA or the genomic coordinate is, and I've pre-populated that with the transcript from the lab report and the specific variant that we found in MYH7. We'll convert that to the genomic coordinate, which is again listed here. Again, it's swapped the specific nucleotides based on the appropriate strand, and you can see I've just copied the specific genomic coordinate of that variant and put that in to the search here, and unfortunately it looks like this one isn't showing up either. So the question will be whether this is not represented in the database because it's not present or because coverage is poor. The graph at the top suggests that the coverage across the most of the MYH7 gene is fairly good, but let's go ahead and test that. And there's one way to search that we haven't discussed yet, which is variant specific. So rather than searching the table manually or using a find search, you can just click on one of the variants and you'll see the setup of one that's present. So basically the way you do this is their main URL, variant, / and then the chromosome location, the genomic coordinate, and then the wild type and the variant. And so in this situation, we'll be pasting in the variant found by Mutilizer, and then an A to a C. Forgive me here. Okay. And this essentially tells us that the variant was not found in EXAC, and you can see that the coverage of this region was in general quite good. The mean and median depth of coverage is between 80 and 90. And so that suggests that this is a very rare variant that wasn't missed because coverage was poor, but wasn't present in a large population of 60,000 plus individuals, 120,000 plus alleles. And so that's an example of a rare variant. Unfortunately, this is consistent with what was reported by the laboratory as well. So this variant has not been published in literature or present in population databases. Last but not least, we'll review one more variant that was found in a patient with a suspected diagnosis of long QT who had experienced a cardiac arrest. This was the report received by a third lab that was found in this particular patient. You can see again gene nomenclature you're all familiar with, and in this one the variant, the transcript used for that gene by this particular lab is put not in the method section but within the interpretation section. So this is old stuff. You put the gene in the browser search bar as usual, and this will pop up. One thing that stands out about the KCNHQ is, KCNH2, is that the coverage of each of the exons is not nearly as high as you saw for some of the other variants that we previously looked at. Some of them actually are quite poor and less than 10x. So keeping that in mind, we use the same method as before. We take a look at the lab report and pull out the variant location by amino acid, and that was an alanine 913. And so we'll go ahead and search. And it looks like there is a synonymous variant listed at that location, but this isn't the same one, obviously, that we found in our patient. We can click on it just to take a look at what we're seeing in this particular variant. And it looks like you can see, based on a warning that they put here, that the variant's only been covered in less than 4,000 individuals because the coverage and depth was not adequate, and you can probably see that in the genotype quality metrics. And if you contrast that with what we saw before, the depth is less than 10% for the majority of the participants or the majority of the patients in this database, whereas before we were seeing more of a distribution that was skewed this direction. So this still isn't our specific variant, so we do what we did before. And so using the same methods as before, you plug in the variant location to find out whether or not this was present. This specific variant is present. Now, since we searched and that location was covered this way, I'm presuming it's going to be the same, but let's go ahead and just double check that. And so it does not appear as though that specific variant was reported based on the genomic coordinate. Obviously, the same amino acid appears to be affected with the synonymous variant, but not this specific one at the DNA level. So we will use the same tactic we did before, which is to look at the specific variant location and take a look at whether or not there's any data on the coverage in particular. And that would be using this information. So it's a G to an A. So we'll just change that here. And then similar to the MYH7 case, this variant was not found in EXAC. And in contrast to the MYH7 case, the coverage of this particular variant location is quite poor, which may explain why it wasn't present. So it's one thing to keep in mind, and in contrast again to MYH7 variant we previously did where the coverage was quite good. The question would be whether or not this is a rare variant because it's not present in the general population, or whether or not it's appearing to be rare, but it may be more common, but the coverage by next-gen technologies, usually what these databases are full of, is not good, and so it wouldn't be detectable even if it was a common variant. And so in situations like this, you typically have to rely, if available, on any publication or other databases that use a different sequencing technology, like say, for example, Sanger sequencing. Although I primarily use Mutilizer in my own clinical practice to look up the genomic coordinates of a location, I've also been told about another option, which is referred to as a variation reporter, which provides even more detailed information for a variant, including the links to ClinVar and other resources. So I'll walk through how that works as well. Again, you want to make sure that you're using the proper genome assembly. In this case, the MYH11 variant and the other variants are reported using 37. And so in order to find the genomic coordinates for a particular variant, you need it in the same format as Mutilizer does, which is the transcript followed by the DNA nomenclature. So I've copied that to a Word document for convenience sake, and then you simply need to add it in that format. Again, the transcript colon followed by the cDNA nomenclature. Be careful not to leave a space in between here, because unlike Mutilizer, this does not adapt to that well. And then you just upload. And once that's complete, you submit for analysis, and you can probably run more than one of these. Again, I haven't used this program very often. However, it does give you a variety of information that can be helpful. One is what you entered. The genome coordinates are listed here, and again, and the strand that matters for this particular variant. The chromosome location, a link that takes you to the reference SNP, DB SNP, 1,000 genomes frequency. I imagine if there's some links in PubMed that may be included, the consequence from a molecular basis, etc. And so just to demonstrate there's an alternative way to get the genome coordinates, if this happens to be a resource that you use more often, this is one to consider.